Volume of spheres. So, the volume of spheres. Cavalari's principle says that if solids have the same cross-sectional area, then they have the same volume. Um, so this is the idea that okay, if you have two cylinders, they have the same circles throughout. They're going to have the same volume, but it can be applied to other things, and we're going to use that in order to find the volume of a sphere. And my claim is going to be that the volume of a sphere plus the volume of a cone equals the volume of a cylinder if they all have the same radius and the height is going to be twice the radius of the sphere. So what you're seeing is this, and I'm going to animate this so that you can see the values changing. So what I'm claiming is that the three volumes add up, and specifically that at every point, this circle plus that circle equals the whole circle over there. Same thing here. I'm claiming that that circle plus that circle equals that whole circle. It's kind of hard to see. We'll zoom in. I'm claiming that those two circles add up to the third circle on the right. So, why would this be true? It's a pretty bold claim. So the idea is that if we look at the measurements on here, we can, no matter what circle we're looking at on the sphere, we can form a right triangle. We can say straight up is going to be B, straight right is going to be A, and then that gives us C, which is also known as the radius of the sphere. Well, because C is the radius, it's also going to be the radius of the cylinder. It's also going to be the radius of the cone, but we don't care about that as much. If we look at the same height on the other two shapes, B will be the same on the cone, and because the cone has the same radius and height, this B will have to be the same as that B. The ratio of radius to radius is the same thing as the ratio of B to B. So this represents the radius here, that represents the radius there, and A is the radius of the circle that we're looking at the cross-section of. So in other words, we can say from this right triangle, A squared plus B squared equals C squared because it's a right triangle. Then, once we have the right triangle, we can multiply it by pi to say, okay, pi A squared plus pi B squared equals pi C squared. So, in other words, this circle plus this circle equals that circle. So we have that the circles add up, and if the circles add up, the volumes should add up. So the volumes of these three things are adding up. Based off of the volumes adding up and the different radii, we can say that this is 2/3 pi r cubed. The volume would be 1/3 of a cone is regularly 1/3 pi r cubed, but because there are two of them, there's the one at the top and the one at the bottom. That's why it's turning into 2/3 pi r cubed. And then the cylinder, this is r and that's r. So we have the pi r squared h. H is 2r. So then this becomes 2 pi r cubed. So now we have this equation. Performing algebra on this, subtracting 2/3 pi r cubed from both sides. Sorry, 2/3 pi r cubed from both sides. 2 minus 2/3 is 4/3. And our answer, the volume of a sphere, and this is actually the proof of the volume of a sphere, the volume of a sphere is 4/3 pi r cubed. So that is the formula that you'll need, and we can apply it quite straightforwardly. 4/3 pi r cubed. 4/3 pi r. Is not 20. R connects the center to the side. R is 10. So 7 cubed is 343 times 4/3 is 1,372 over 3 pi. And if you want the decimal answer, it would be about 1,437 cubic miles. Here, 10 cubed is 1,000, so you get 4,000 thirds pi. And if you want the decimal answer, we get 4,189 cubic miles, or sorry, cubic meters. That's how we find volume of spheres.